Why do we still struggle to solve complex problems? We have mapped the entire human genome, yet we still don't fully understand diseases and human evolution. Why? We study and analyze economic policies, yet financial crises and wealth gaps continue to persist. What's the reason? We try to improve education by focusing on test scores, yet students' motivation and creativity often decline. Why? The reason is simple. We focus only on individual elements, but fail to see the whole system. Most problems in the world do not stem from a single cause. They arise from a vast interconnected system where multiple elements influence each other, creating unexpected consequences. Today, we'll explore systems thinking, a powerful way to deeply understand complex problems, predict unintended consequences, and design better solutions. So get ready to see the world from a new perspective. When we try to understand the world, we often rely on analytical thinking, breaking a problem into individual parts and analyzing them separately. This approach has been useful in physics, chemistry, and even genetics. However, it has limitations in understanding biological phenomena. Why? Because living organisms are not just a collection of independent elements, but complex systems created by interactions between those elements. According to Bert and Lamphey, a system is not a set of isolated components, but a dynamic and interconnected structure where elements influence each other. In other words, life systems exhibit characteristics that cannot be seen when looking at individual parts alone. Their structure and function emerge from the interactions within the system and their relationship with the environment. So how does systemic thinking differ from analytical thinking? So analytical thinking breaks a problem into individual elements, analyzes them separately, and combines the results to understand the whole. For example, studying human DNA sequences or analyzing cells to understand human biology. On the other hand, systemic thinking focuses on relationships and interactions between elements rather than isolating them. For example, to understand humans, we must not only study DNA, but also how it is expressed, how it interacts with the environment, and how cells and tissues function together. This isn't just a theoretical difference, it's crucial in the real world, where many complex problems cannot be explained through simple cause and effect relationships. So what are the key principles that make up systemic thinking? The first is to recognize dynamic processes. Systems change over time, so we must consider long-term effects, not just immediate outcomes. Second is to understand interactions. Elements within a system influence each other, making isolated analysis insufficient. Third is to identify feedback loops. Systems contain positive feedback loops, amplification, and negative feedback loops, regulation. For example, one reason global warming accelerates is because melting ice reduces the Earth's reflectivity, causing more heat absorption, which is like a positive feedback. The other important process is to recognize cyclical relationships. In systems, effects are not always linear, but cyclical. For example, a new education policy may aim to improve student achievement, but could increase test pressures, leading to reduced creativity. Also, the other important process is to acknowledge delayed effects. When one element affects another, the impact may not be immediately visible. For example, the environmental damage caused by pollution may take decades to become apparent. The last process is to consider nonlinear complexity. Small changes can lead to large effects, sometimes creating unintended consequences. So how can systemic thinking be applied in the real world? Especially, how can we apply the systemic thinking in education? Improving test scores alone does not mean improving education. We must analyze student motivation, teaching methods, and education policies as a whole. For example, memorization-based education may boost test scores in the short term, but can reduce creativity and problem-solving skills in the long run. And the same principle applies to solving environmental problems. Environmental issues cannot be solved by simply eliminating one cause. They require a systemic approach. For example, banning disposable cups may reduce plastic waste, but the increased use of reusable tumblers could lead to higher carbon emissions during productions. The systemic thinking applies well in healthcare and public health systems as well. Instead of treating diseases, focusing on prevention and long-term health maintenance can be more effective. So for example, reducing obesity isn't just about promoting exercises. It requires addressing diet, stress, and socioeconomic factors. So how can we train ourselves to think systematically? We first have to practice seeing the whole picture. Instead of just analyzing simple cause and effect relationships, consider how multiple factors are interconnected. And also we have to train ourselves to think in cycles. Please ask, what are the long-term consequences of this decision? And also we have to consider multiple perspectives. Don't just settle for a single solution, but explore various possibilities. And we can also use various simulations. One of the best ways to apply systemic thinking is to experiment with different variables and observe how changes affect the system. Today, we explored what systemic thinking is, why it matters, and how it can be applied in real life. The next time you encounter a complex problem, don't just look for a single cause or solution. Instead, consider how different elements interact within the system and how they influence each other over time. If you found this discussion helpful, please don't forget to like, subscribe, and share your thoughts in the comments. I'll see you in the next time with better content. Thank you.